The sun just did something it hasn't done in months, and scientists tracking the fallout say this week is shaping up to be one of the most active stretches of space weather we've seen since the current solar cycle approached its peak. 3 separate disturbances, each with a completely different origin and a completely different mechanism, are converging on Earth within the same 7-day window, and the overlap itself is what's catching researchers' attention. This isn't one storm followed by a quiet lull. It's 3 distinct sources of disruption stacking on top of each other, and today we're going to break down exactly where each one came from, how they're interacting with Earth's magnetic field right now, and what that means for satellites, power grids, and anyone hoping to catch the Aurora over the next few nights. Let's start with where this actually began, because the story of this week's activity traces back to a single, unusually complex region on the surface of the Sun. About 5 days ago, a massive sunspot cluster rotated into an Earth-facing position, a region researchers have been tracking under the designation AR4493. What makes this particular sunspot group stand out isn't just its size, though it is large enough to be genuinely one of the more significant active regions to cross the solar disk this year. It's the magnetic complexity underneath it. Solar physicists classify sunspot regions using a system that describes how tangled and unstable their magnetic fields are. And AR4493 carries what's known as a beta-gamma-delta configuration, essentially the messiest, most unstable arrangement on that scale. Regions with that kind of magnetic complexity are the ones most likely to snap, twist, and release their stored energy in sudden, powerful bursts. And that's precisely what AR4493 has spent the last several days doing. Here's what makes this genuinely unusual. In a single recent 24-hour stretch, this one region was responsible for the overwhelming majority of all flare activity recorded on the entire Sun, firing off more than 20 separate eruptions, including a moderate to strong M-class flare in the mid-M range. 2 of those eruptions launched coronal mass ejections. Enormous clouds of charged solar material and magnetic field blasted outward into space, and both of those clouds happened to be aimed almost directly at Earth. That's disturbance number 1 and disturbance number 2. Both born from the same unstable sunspot region within roughly a day of each other. Think about what a coronal mass ejection actually is before we go further, because understanding the mechanism is the key to understanding why this week looks the way it does. When a tangled magnetic field on the Sun finally breaks, it doesn't just release light and radiation the way a flare does. Flares travel at the speed of light and reach Earth in about 8 minutes, arriving before scientists even have time to issue a warning. A coronal mass ejection is different. It's an actual physical cloud of plasma, billions of tons of solar material thrown outward at speeds that can reach several million kilometers an hour. That cloud takes 1 to 3 days to cross the 93 million miles between the Sun and Earth, which is exactly why forecasters can watch it coming and issue advance warnings, unlike a flare, which simply happens and is over before anyone can react. Now here's where the third disturbance comes in, and it has nothing to do with AR4493 at all. Separately from the flare activity, a massive coronal hole. A dark, cooler region where the Sun's magnetic field lines open directly out into space rather than looping back down to the surface, rotated into an Earth-facing position around the same time. Coronal holes act like open valves, letting a continuous stream of high-speed solar wind escape far faster than the slower background wind surrounding it. This particular hole stretches across both solar hemispheres, making it one of the largest structures of its kind to line up with Earth in months, and it's been pushing solar wind speeds up toward roughly 700 kilometers per second, more than double the typical background speed. When that fast stream catches up to and slams into the slower wind ahead of it, the two compress together into what scientists call a co-rotating interaction region, a dense, turbulent wall of solar wind and magnetic field that behaves almost like its own miniature storm system when it eventually reaches Earth's magnetosphere. So that's the full picture. 2 Earth-directed coronal mass ejections from the same unstable sunspot region, arriving as glancing blows rather than direct hits, layered on top of a compressed high-speed stream from an unusually large coronal hole. 3 separate physical mechanisms, 3 separate origins, all converging on the same planet in the same week. That kind of overlap is exactly why researchers describe this as a genuinely active stretch, rather than just another routine update. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of space weather coverage reach more people who are actually curious about what's happening above our heads. So what has actually happened as a result, and where do things stand right now? Earth's magnetic field has been swinging between quiet and active conditions for the past several days, with the planetary KP index, the standard scale scientists use to measure geomagnetic disturbance, bouncing between 2 and 4 on quieter stretches and briefly touching 5 during the more active windows. On the standard G scale that forecasters use to communicate storm severity to the public, That translates to minor G1 level geomagnetic storming through most of this stretch, with brief, moderate G2 level conditions possible during the strongest compression periods. To put that in context against what this same active stretch of the sun produced just a few weeks ago, an earlier eruption from a different, now rotated away sunspot region triggered a much stronger G3, strong level storm that pushed Aurora as far south as New Mexico and lit up skies across roughly 30 states. A reminder that this same general period of solar activity has already proven capable of punching well above what forecasters initially expected. This week's activity, by comparison, is running at a more moderate level. But the multiple overlapping sources are exactly what's keeping conditions elevated for a longer stretch than a single isolated event typically would. It's worth pausing here to correct something that tends to spread quickly whenever headlines mention multiple solar storms hitting at once. This is not a Carrington-level event, and nothing in the current data suggests anything close to the kind of extreme, infrastructure-threatening storm that ranks at the very top of the severity scale. Severe and extreme storms, the G4 and G5 categories, are capable of triggering widespread power grid problems and significant satellite disruption. What's unfolding this week sits several rungs below that, in minor to moderate territory. The reason it's getting attention isn't the raw intensity of any single component, it's the layered, multi-source nature of the disturbance and the fact that it's happening as the sun sits near the peak of its current 11-year activity cycle, a period when this kind of overlapping activity becomes meaningfully more common than it would during quieter years. That distinction matters when we talk about who actually feels this and how. For satellite, operators running spacecraft in low Earth orbit, elevated solar activity heats and expands the upper atmosphere, which increases atmospheric drag on anything orbiting through it. That means more frequent orbit corrections and closer tracking of potential close approaches between satellites and debris, since objects sink through their orbits slightly faster than usual during active stretches like this one. For power grid, operators, particularly in high latitude regions like Scandinavia and northern Canada, the concern centers on geomagnetically induced currents, extra electrical current that a disturbed magnetic field can push through long transmission lines, occasionally triggering voltage alarms or requiring operators to adjust transformer loads as a precaution. For aviation, high-frequency radio communication used on polar and transoceanic routes can experience temporary fading or blackouts during the more active windows, which occasionally leads airlines to reroute flights away from the highest latitudes for a few hours at a time. And for anyone relying on precision GPS, whether that's agricultural equipment, marine navigation, or surveying work, positioning accuracy can degrade slightly during the peak hours of disturbance, usually recovering within a matter of hours once conditions ease. Then there's the part of this story most people actually came here for, the aurora. When the interplanetary magnetic field carried within these disturbances tips into a sustained southward orientation, it essentially unlocks a more direct connection between the solar wind and Earth's own magnetic field, allowing far more energy to pour into the upper atmosphere and drive the aurora further from the poles than it normally sits. Over the more active nights this week, forecasters have flagged a realistic chance of aurora visibility across the northern tier of the United States, including states like Washington, Wisconsin, and Michigan, along with a wider band across Scandinavia, Scotland, and northern England. Whether that visibility actually materializes on any given night depends heavily on that magnetic field orientation, something that can only be measured with any real precision once the solar wind is already washing past monitoring spacecraft stationed roughly 1 million miles from Earth, which is part of why aurora forecasts even a day out always carry a fair amount of uncertainty attached to them. If storm coverage like this is something you want more of the moment new activity develops, subscribing means you'll catch the next update as soon as the picture changes. Zooming out from this particular week, there's a broader pattern worth understanding, because this isn't happening in isolation. The sun is currently near the peak of solar cycle 25, the roughly 11-year rhythm of rising and falling magnetic activity that every star like ours cycles through. During solar maximum, large complex sunspot regions like AR4493 become far more common. Flare frequency climbs sharply compared to the quieter years on either side of the peak, and coronal mass ejections aimed squarely at Earth happen with noticeably more regularity. That's precisely why this year has already produced multiple strong storms, including the G3 event from earlier this month, and why forecasters are treating weeks like this one as something closer to the new normal for the current stretch of the cycle rather than a rare anomaly. There's also a genuinely important technological shift sitting underneath all of this that's worth understanding, because it changes how much warning we actually get. Earlier this year, a new spacecraft called Solar 1 took over as the primary solar wind monitoring satellite, stationed at what's known as the L1 Lagrange point, a gravitationally stable spot roughly 1 million miles from Earth directly toward the sun, replacing an aging predecessor that had been running well past its expected lifespan. Solar One carries a new instrument capable of detecting coronal mass ejections while they're still relatively close to the Sun, 1 to 2 days before they reach Earth, giving forecasters meaningfully more lead time than earlier generations of monitoring equipment ever could. That upgrade doesn't make storms any less powerful when they arrive, but it does mean grid operators, satellite controllers, and airlines get a longer runway to prepare, which matters enormously even when the storm itself sits at a moderate rather than severe level. Bringing this all together, what's playing out this week isn't one dramatic single event. It's 3 separate physical processes on the Sun lining up almost perfectly in time. 2 coronal mass ejections born from the same unstable, magnetically tangled sunspot region arriving as glancing blows rather than head-on impacts, layered against a compressed, high-speed stream pouring out of one of the largest coronal holes to face Earth in months. None of this rises to the level of a severe or extreme storm, and none of it poses a serious threat to daily life for most people on the ground. But the overlap itself, 3 distinct sources of disturbance hitting in the same short window, is exactly the kind of pattern. Scientists watch closely because it's a clear signal of just how active the Sun has become as it sits near the peak of its current cycle. If you're in one of the higher latitude regions where aurora chances are elevated over the coming nights, keep an eye on real-time forecasts rather than assumptions made days in advance, since the magnetic orientation that determines visibility often isn't clear until the solar wind is already washing past monitoring instruments close to Earth. For satellite operators, grid engineers, and anyone working in fields sensitive to space weather, this week is a reminder that solar maximum isn't a single dramatic event. It's a sustained stretch of exactly this kind of overlapping, layered activity. And for the rest of us, it's simply a good week to glance upward after dark, because the same Sun that's keeping scientists busy behind the scenes might just put on a show that's easy to see with nothing more than a clear sky and a bit of patience.